Well, hello. I've been asked by Nora to talk about what I've been working on lately, and we've recently had sort of a minor breakthrough. Things are starting to sort of kind of work, and so I'm happy to do that. I also am going to try to avoid the situation that I found myself in every once in a while with these talks where, you know how research is, right? You find sort of a general topic and then sort of a sub-area of that topic and then a little someone else's work in that topic and then a little slice of that and then a little tiny little extension of that you could work on, right? And then sometimes when people give talks about that, they're like, well, let's start here and then talk about what I've been doing. I'm going to try to start a little bit farther back so that if you maybe haven't been living and breathing lattice creep spatial models, then this will still be okay. Spatial modeling in the ACS data. So spatial statistics, well, you know, ACS, American Community Survey, that's basically a Census Bureau product. And we've been working on using a creating model, specifically the lattice creating model, to talk about a different type of data that it typically is applied to, right? So, we'll get that here. A little bit of information about the ACS. It's been ongoing for decades now. It's run by the Census Bureau. It studies a lot of things, but if you want to classify them in terms of broad topics, ancestry, education, income, language, migration, disability, employment, and housing characteristics, but we're talking a fairly broad set of variables here, right? If you were to download all of the ACS public data report, you would have tens of thousands of variables. There's lots of stuff in there. In terms of the scale, it's a fairly large survey, right? It's ongoing. It's always being gathered. It's about 300,000 households every month, which nets to about 3.5 million American households surveyed in the course of a year. And their public data product. They actually provide data products for government agencies as well, but their public data product is released annually. Contains estimates of thousands of variables over several temporal and geographic aggregation levels. So. While this is a large sample, it's actually not a very large sample relative to the geographic fineness that they actually approach this to.
Is it the same 300,000?
It is not. No, it's not quite independent sampling term to term, but yes, not the same group every time. which is required, because if you're talking about these lowest level geographic geometries, states, of course, 51 if you count DC. Counties, so a couple thousand in the country. Tracts, a couple thousand in some of your typical states. Blocks, these are, census blocks are really pretty tiny, right? Hundreds of people living in a census block. Typically several thousand in a tract, right? And so if you think about 320 million Americans, it takes a lot of these geometries to parse those. But we'll see what those look like. Additionally, they generate these estimates based on these relatively small samples for these relatively small geometries by aggregating across multiple years of survey results. And so what happens is you get lots of data if you're willing to accept some data that might not be quite so new, or you can get really current data, but it might not be available at the geometries that you're interested in. So this is the sort of thing that you can get. This is the second smallest geometry size that's available in the public product. These are so-called census tracts. Tracts were originally designed to have between 2,500 and about 8,500 people in them. And they were also selected to identify sort of a neighborhood, right? So they're supposed to be sort of culturally similar as opposed to just being a chunk of land. But they were drawn up decades ago, and so the population range is a little bit broader now, and of course, they're not all just cohesive neighborhoods anymore. But that was the idea of these things, right? They were not designed to be random parsings. They were designed to take advantage of sort of the identity of the fundamental shape, right? the culture, so to speak. This, of course, this actual geometry is not from the ACS itself, but it's also from a census product called the Tiger Lines website, where you can basically find the shape files that correspond to the geometries that the ACS uses, right? So there are tools in R, tools in some other software that's not R, but I don't care about because it's not R. So, but yes, basically this stuff is really easy to handle in R. There's lots of libraries. You can just import the Tiger Lines file, line it up with your ACS data file, and plot things very easily, right? So this plot, of course, I had to import the data, import the tiger lines, and then set up the scale. This is generated with like 10 lines of code. This is not like impressive rough stuff. This is just fast, easy stuff. People have been doing this a long time. But you can sort of see that you've got relatively fine grades here on this geometry. These are census tracts. This is North Carolina. It's of course traditional when you're doing spatial statistics because the Cressy book did talk about North Carolina, right? Those of you who have read the Cressy book know that he goes on for about 3/4 of the book, the NC SIDS data set, right? So I like North Carolina. I like it for another reason. That is, you don't get to cheat as much with your geometry, right? If you look at, say, Wyoming, it's like, oh, a nice rectangle. What about the counties? Smaller rectangles. Okay, well, this at least is nice. It's also nice in that it has multiple major metropolitan areas, right? So you don't have to worry about there being just one hot spot and then everything else is cold. So North Carolina is nice for a lot of reasons, mainly so that you're not cheating. Anyway, this is sort of the shaded areas here are areas where you actually have data for those census tracts on this particular income variable, so median household income by tract, 5-year estimates. You can't really tell, but the palest ones here, this guy, that little guy there, some of these guys, these are tracts for which estimates are not published. The ACS will not publish estimates if two things occur. Either A, they just didn't look at it at all over the time frame that you're interested in, which over the 5-year estimate, that's none of them. They try to make sure that they get every tract at least once in the 5-year period. Or B, they studied it, but the margins of error were so large that they just didn't feel comfortable even publishing their estimates. So these guys are areas that they did have data, but they're not sharing it with us because it's low confidence data. Right? In general, for the 5-year data, just a sort of a loose survey I did, typically for a given state, you'll have upwards of 99% of the tracts for 5-year data. When you get down to sort of the 3-year margin, we start to talk about being between like 40 and 70% of the tracts being available. And when you start to get to the 1-year margin, that is the most recent data, things go down pretty rapidly. Depending on what state you're in, you can have between like 5 and 25% of tracts available. So that brings us to the motivating problem here. We have all of these individual observations for all of these regions except for like that one and that one. And you're looking at this and you're saying to yourself, well, I might not be a spatial statistician, unless you are, in which case, cool. But you can look at this and you say, look, there's clearly some sort of spatial structure here. All right? So if you were doing sort of naive statistics, and you said, I want to estimate what the median household income is in that missing county, right? Naively, you just say, well, what's the average for all the rest of the counties in the state, or something like that, which is a way to go about it. But of course, if you're more spatially inclined, you might say, well, what if I take a little average of these guys, the ones that are close to it? Right? That's another way of going about it. We try to do something a little different that actually lets us handle this kind of problem in a different way. But that's our goal. We have missing data points in sort of this aerial data, right? This data that's tagged to these individual regions, and we want to estimate those missing values. Yeah, problem, right? So basically, on the short term, you don't have as many as you like, right? So the example here in 2016 product that was released, 5-year estimates just for total population, right? A pretty simple thing to measure, well, relative to some of the other things they measured. In Colorado by county, all 64 counties in the state have an estimate for them. But when you go down to the 1-year measure, you only have 12 counties covered, right? And so you're talking about less than a quarter of the counties available all of a sudden. So you want to estimate what's going on in, for example, Weld County, you're lucky that's in there. But you go next to Weld County, you go north a little bit, all of a sudden you've lost your estimate in terms of the short-term data. So we're going to try to predict the missing geographic regions by taking advantage of that spatial structure. So, those of you who haven't taken spatial statistics, you don't need to know a lot about it. There's a lot to it. Spatial data, in terms of the sort of the statistical context, is a pretty broad term. These are data where you have both actual values that you care about, right? Median income, total population, and actual spatial locations of those observations. So it's not just a data set, it's a data set where you know where the observations came from in one way or another, right? There's all sorts of different types of spatial data. The two that are sort of relevant to what I'm doing here are what are called point reference data. And it's exactly what it sounds like. It's data that refer to a specific point in space. That is, this particular example, at this exact location on the surface of the Earth, we have a measurement. Right? So that's not spread over a region. That's saying at that one physical location, we have this measurement. And that's, of course, not what we're working with ACS data. Although people have done this, people have taken the attempt to model this data by saying, let's say that this value is actually located at the centroid of that shape. And then say now it's a point reference data. I don't like that. It makes me feel gross. So,
Is your data, is it a number or is it a range of income?
the data are typically actual numeric values plus estimates of the margin of error. Yeah. So this is just plotted by Stein because the graph is nice that way. But yeah. The data are typically not by quantile, though some of them are. Right, so point reference data, it's nice because, you know, part of that random element is taken away. You know where it was, and you have to figure out what that measurement is and what the error is, but at least you have that physical specific location. Then there's what's called lattice data, which is an unfortunate terminology given that we're talking about lattice kriging, and that's a different lattice, but we'll deal with that as we get there. Lattice data refers to data observed over a countable collection of spatial regions. Right? And so that's what we have with the ACS data. Right? We're talking about observations that are tied to areas, or volumes if you're doing this in 3 dimensions, or intervals if you're doing it in 1. Right? So instead of them being associated with a specific point location, they're sort of smeared across a bunch of them. Yeah? Okay. With point reference data, there's an entirely different set of analysis tools available than, of course, with lattice data, right? So point reference data, you're sort of thinking of things as being observations of some underlying surface. That's sort of the common modeling approach. But with lattice data, this ends up looking like a lot of graph theory, right? You basically say, okay, well, how can we model this lattice? Well, let's say, okay, let's define a neighborhood structure and say, okay, well, this area is a neighborhood of this one, and 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 then define your covariance structures based on neighborhoods, which is fine. We took a different approach, though. So our goal, the thing we're trying to do, is use a really cool tool for this type of data that's relatively recent, right? The main paper on it's from 2014, and apply it to this type of data. So first we need to talk about kriging. Kriging is named after a South African mathematician who started working on the Krige, so K-R-I-G-E. So this,
He was mining.
yeah, he was enough of a mathematician to get enough done. But yeah, he built this system for one of the mining concerns of South Africa. Yeah, if a guy's going to build a regression technique, I'm going to let him be called a mathematician. I'm going to allow that.
He might regard that as an insult.
Well,
Like heavy side and Fourier. Neither.
Mathematicians.
fair enough. All right. Krieg is a guy who built I'm going to call it a regression technique. It's very similar to the regression techniques we've seen before, but it's not quite the same. Basically, so kriging, though it sounds like sort of, there's no E in there, right? We're not kriging, it's just named after a guy. One modeling approach, this is sort of one formulation of it, is to say that these observations that we're seeing in space, and we're talking about point reference data here, right? These observations that we see in space, so S is a location in space, we're saying that those are actually noisy realizations of some underlying surface. Right? This is one formulation of a more general, like random function kind of model, right? You're saying you have some function, your observations of that function are random realizations, and unfortunately in this context we're basically saying we have one observation at a given point, so you can't really estimate the function in the traditional ways, right? To do this estimation, you typically need a sample of at least size 2, and we have observations of size 1 at any given point in space, and there's uncountably many points to worry about, so it's gross. So you have to put some structure on this thing. So typically we say, okay, let's make some assumptions about the structure of these errors, right? And those assumptions, are they Gaussian? Of course, we know that making that assumption is usually ridiculous, but super helpful most of the time. And we're going to make that assumption if we're kriging. Right? Kriging is in the Gaussian framework. Then there's really the question, what's the form of the covariance between these errors, right? The thing that we can exploit in spatial structure is that you have these errors that are not necessarily independent of one another. So the question is, how does an observation at one point in space correlate to an observation that's near or far or even farther away? And if you're taking spatial statistics, you'll talk about things like stationarity, which talks about how the patterns of covariance you think they might behave, right? So does covariance depend only on the distance, for example, or does it depend on the distance and direction, or is it, is it sort of an elliptical? Like there's all sorts of assumptions you can place on this covariance structure, not really important for the purpose of this talk, but this is basically Krieging says, let's make a certain set of assumptions about this structure, and then assume and basically then fit what f of s should be from those observations and our assumptions. So, just to be clear, so Krieging, the typical inputs to Krieging are, of course, point observations of values, right? So you have locations and values, right? So this is the sort of data you collect. You go out with your sensors and you say, okay, well here it's this, here it's this, here it's that, and so on, right? So that's sort of our inputs. The outputs that you get when you Krieg are twofold. One, this is that surface that you're interested in, right? And in a sense, this is sort of the mean surface, right? Because you're assuming this is a random function. You want to know what the mean is, right? What's the mean value of that thing? And so, of course, you see that this guy is sort of it's basically just an interpolation of the values here, kind of, sort of, right? Under some assumptions. So you got some elevated levels here. Well, that corresponds to a hot zone over here. You got some cooler levels down here. It's cooling off over here, right? But the other thing that Krieging gives us with those covariance assumptions is this guy. This is an uncertainty surface. This tells you, okay, you have an estimate of the mean. How confident are you in that, right? And so this surface actually over here combines a couple of things. First of all, how far are you from an actual observation? Obviously, the farther you are from a sensor station, then the less confident you're going to be. But also, how dissimilar from the surface are your observations, right? Like how far are your observations from what you think the surface is, right? What's sort of the variability of the surface itself? What's the covariance structure you've assumed based on the things? And so this incorporates all of those measurements. And so what you see here is, where you have a lot of points, they're all pretty close to each other, and in terms of both physical location and in value, that generates this region where you have fairly low uncertainty, right? You're pretty confident in your predictions here. Whereas,
what are you plotting? What is that?
this guy, it's the Krieging standard error.
A standard.
Yeah.
So, where is the Gaussianity used?
The Gaussianity comes in the process by which you model the interpolation between the points. For typical Krieging, it's gross and I don't quite understand it. For lattice Krieging, it's a little bit, it's also gross, but I understand a little bit better. Gaussianity comes in terms of the coefficients that are associated with the components of this function. There's a slide for it in a couple.
Okay.
Right. But anyway, so these are sort of like the typical inputs and outputs of a Krieging process. It's important to note that if you're using like traditional Krieging, that's been around for a while, like if you use R's M Krieg function, if you're talking about 153 observations and you want to Krieg that, you're talking about minutes of work. If you're talking about 1,000 observations, you're talking about half an hour of work. If you're talking 10,000 observations, you're talking hours and hours of work. Right? M Krieg is not quick. However, lattice Krieg. This is the new work that Doug Nitschke and Schmidt, of course, have been working on, which is to basically say, okay, let's make some further assumptions about this underlying surface that we're working with, right? And so those assumptions basically say this underlying surface, this f of s, has this basic structure. And this basic structure has three components, right? So this n of s, all this is a low order polynomial, right? So basically you can think of it as like a plane in space that everything else is sitting on top of. ZD, this is just traditional like covariate regression stuff. This is not spatial. This is like, okay, I want to regress out minority status or income level or other things from the actual variable I care about, right? So this basically just does linear regression, and then you fit the rest of this on the residuals. This guy is where things get interesting. That is a basis function representation, and those basis functions, those phi's, those are actually multi-resolution Wendland radial basis functions. So, this guy is basically saying, okay, we're going to take the surface, we're going to say there's a simple polynomial part, there's some spatial covariates, you don't really need those if you don't want them, right? I'm not going to use them in the test problem. And then there's this guy. These guys, I don't know if you've seen Vindlin functions before, but they're basically polynomials that then get trimmed out at 0. They basically hit 0 at a radius of 1, and then they're 0 out from there. So they have compact support. And the thing that Gaussianity gives us, these coefficients. We assume that these coefficients follow a Gaussian Markov random feed. So when we fit this guy, we specify the order of the polynomial, we tell it what the basis functions are that we want to use, and it goes through and it fits the coefficients for the polynomial and the coefficients for the basis functions based on our observations. And some other things. Yeah. All right. It's multi-resolution. This is not just one layer of identical basis functions that are translated across space. You can do it that way, but we found that you get better results if you have multiple resolutions. That is, you have one sort of coarse grid of big fat basis functions, a few of them over the entire space, followed by a finer grid that's twice as high with functions that are twice as small in terms of their extent. And I like to use 3 levels myself. 4 gets pretty computationally intense. 2 tends not to really catch all the surface contours that I'm interested in. But the only limits on this are your hardware. Right? So yeah, it's basically 2 levels. And the thing that's cool about this is each level you take to be independent of each other. So when you're doing the fitting, you specify what weight you want to apply to which level, and it'll fit accordingly. I typically just do equal weights unless I have a reason not to. Right? If I think that there's some really tight contours that I want to catch, I overweight the fine levels. And if I'm interested in just the broad, long-term surface, I overweight the coarse levels. But it's not real critical. It is kind of critical, but not super complicated.
Can you explain exactly what you mean by Markovian in this context? In other words, you're talking about independence with respect to what?
So the covariant structure that's sort of assumed on these guys is all right, so if you got your grid and then you've got like this basis function and this, well, the centers are arranged on just a regular lattice, right? Which is why this is called lattice grid. The assumptions we make on the covariance are that sort of the associations here are this one is associated with this one, and this one, and this one, and this one, and that's it.
Coefficients just have one dependence in one.
-1, -1,
Okay,
-1,
got it,
-1, at least 4.
Got it. Okay.
You can set it high if you have a reason to, but yeah.
What values of M have you been using?
For the problem we're going to see shortly is slightly like 2,500. Doug's rule of thumb is for normal kriging, you want to have at least as many basis functions as you have observations. So in our case, we got about 2,200 counties. We use slightly more than that in terms of basis functions. But you don't really set M so much as you set the number of levels you want to use and the resolution of the coarsest level. It sort of falls out from that. All right. Okay. Here's what we've been doing that's weird. We are going to take the Krieg model, which of course is all about these surfaces, and we're going to try to see if we can model aerial data using the integral transform on these surfaces. All right? So basically, the ACS data is lattice data. It's data collected on those regions. Well, let's let those regions be AK. Let's assume and see what we can get out of this, that these observations, these regional observations, are actually integrals over those regions, these are spatial integrals, of some underlying field perturbed by some noise. And let's see if we can actually, through that assumption, let's see if we can take these observations, these integral observations, and estimate F. Because if we can estimate F, then we can actually generate estimates for any custom region we want just by spatially integrating it, right? The thing that's sort of unfortunate about traditional lattice techniques is you're kind of stuck with the geometry you start with, right? You build your neighborhood matrix and you're like, okay, well this county is next to this county, and someone asks you, well, can you estimate for this county and this county together? And you're like, yeah, I can add them. But your covariance structure doesn't really accommodate that, so it's not great. With this approach, once you've got F, any region you care about, you can integrate it and figure out an estimate. So, happily, the lattice Krieg library in R supports a generalized inverse problem architecture that's in sort of a linear context, where if you can figure out this U matrix and this X matrix and express Y as this sum, it will fit D and C and find properties of E. Epsilon, right? So what are these things? U is just a mapping matrix for the coefficients of the fixed part of the model. So in the case that I gave here, right, those are the coefficients for n of s. So if you're just doing like a simple linear function over two space, you have three coefficients, right? The constant, the x term, and the y term, right? So you'll, in that case, U is going to have three columns, one for each of those components. X is, of course, what maps your function onto C, and C is exactly what is in those slides before. C is the vector of the coefficients that go with those basis functions. So X in this context is going to be a matrix that contains the integrals over the spatial regions you care about of every single one of your basis functions. So the number of rows in U and X is equal to the number of observations you have. The number of columns in U is given by the size of the polynomial you're using, in my case just a linear, so 3. And the number of columns in X has to do with the number of basis functions you're using. So in my case, 2,000 some odd, right? So in terms of the size here, we're talking, but for the North Carolina data, we're talking, 2,200 by 3, 2,200 by 2,800. So not small, but okay. The cool thing is that X, of course, is going to be pretty sparse. Those basis functions have compact support. And since they have compact support, most of those integrals over these regions, right, most of the integrals over these regions are going to mostly have zero integral values, right? If you're saying, okay, well, what's the integral of this basis function over all of these other counties? Zeros. And Lattice-Krieg is written specifically to take advantage of sparse matrix benefits, right? So, all right. Let's jump real quick into simulation study because I have been talking a long time, so sorry for that. Anyway, basically this is set up so that this can work on any sort of linear transform. In our case, we have integration, so that'll be our transform. How's it work? Well, I'm going to use the North Carolina geometry, and I'm going to use an underlying function that's kind of interesting, not so interesting as to be very, very poorly performing, but then interesting enough that you can sort of see how it breaks down. X and Y here are basically lat long. You see you got some sort of slow sinusoidal behavior in both north-south and east-west. You got some smaller magnitude, higher frequency behavior, it's periodic. And also you've got sort of this linear trend, right? So it's higher in the northeast than in the southwest. Right? So whether this has anything to do with any actual population variable, no. No, it's just chosen as a gross surface that I can actually integrate relatively easily and then figure out what I can do. Region of interest, the roughly 2,200 polygonal subregions of the census tract geometry for North Carolina. Basic process here, apply. Basically, I assume that my data model is true. And I say, well, let's make a bunch of observations Y by integrating that known field and then adding some noise to it. The noise in this case, I assume to be mean zero Gaussian with a standard deviation equal to about 5% of the average integral value. So that's sort of our baseline, right? Our observations typically are perturbed by about 5%. And that's the standard deviation of the noise that we're putting on. Census tracts themselves, just because, nice. That's what the integrated looked like over that space. Right? This is essentially what we're trying to estimate, but we don't get to see this. Like the regression doesn't see this, it sees those integrals. And in fact, noisy integrals, not even nice integrals. Right? But again, you see sort of that hot, hot, cold, cold, that's that sort of slow sinusoidal behavior. And then you've got these little, dots showing up, that's that high frequency sinusoidal behavior. And then you can't really tell from the geometry, but it's actually slightly higher in the upper right than it is in the lower left on average. But yeah, mathematicians, that's what a graph looks like. Sorry. Okay. Just as that's a projector showing you a bunch of dark areas. Sorry about that. This is basically the tract level integral values of that integrand, right? And so these are coded by the value of the integral over that region. Naturally, tiny, tiny, tiny little regions near the urban centers are going to have smaller integral values just because they're over smaller areas, right? But this is what we got to work with. This is sort of the baseline inputs. not with noise. This is not noise, this is just raw integrals. So how does this thing do? This, of course, is the truth, just so we can see it and compare it. This is just a random sample of 80% of the tracts. I took 80% of the tracts, took their integral values, added noise, plugged them in the regression, and said, predict the surface for me, lattice Greek. Lattice Greek gave me this, which is not terrible. It's pretty good. But 80% is basically cheating, right? 80% is, you're not going to get 80% unless you're looking at the really long range estimates. So how about if we go a little bit further, right? 60%, 60% of the tracks. Sample those at random. What do you get? You can see you're sort of smoothing things a little bit more than you'd like, but that's still pretty nice. Still cheating. 40%. All right, now things are starting to get a little smoother than you'd like, right? Those high frequency, low magnitude signals are starting to get lost a little bit. 20%. Again, it's sort of starting to be a little bit smooth. What if it's 10%? So we take 10% of the tracks, integrate them, add noise, run the regression. This is the surface that lattice Greek spits out. And if you look at those, you see that obviously that sort of high frequency, low amplitude signal has been lost. And of course what happens here is lattice Greek has to estimate that noise component as well. And what's happening here is that sort of short-term waviness, that's getting bundled in with that noise as opposed to being part of the surface, right? So it's part of your estimate, it's not lost entirely. Lattice Greek is then going to say, here are my predictions, but my confidence is actually a little bit lower, right? The standard error estimates go higher, right? Because that sort of gets caught in there. How does that do? Well, that's hard to see, but that's basically the normalized errors on the validation set, or on the training set, and those are the normalized errors on the validation set. In terms of these axes, this is 5% low, this is 5% high. So even based on a 10% sample, if you take that surface, integrate it over all of the regions that you care about, and compare it to the true things that we know because we cheated and made it a toy problem, 5%.
So that means even though you took 10% of the regions, say you were trying to predict regions outside of that 10%, you would still get the quote unquote correct value within 5%?
No.
Okay, then I didn't
Yeah,
understand.
no, you're on the right idea.
Okay.
That's for the training set. This is the
Right.
difference between the actual observed, or basically the true integral values, and the ones that are predicted from the noisy integrals lattice Greek regression.
Okay.
Right? So in a sense, here I'm comparing something to the truth, which you'll never actually know in the real world, right? Naturally, if you look at the errors compared to the observations you plug in, these are going to compact in, but that's cheating. Right? We want to know how these compare to the truth, not our noisy version of the truth that we had to work with.
Yeah.
So this is for the validation set. That is those other 90% of the tracks that we didn't observe.
Yes.
And again, 5%, 5%. So in our worst case scenario, right, our very worst predictions in this particular simulation case are off by about 8%. Which I feel pretty good about, given that I threw 5% error roughly on there just in terms of sampling, and then I'm only observing 10% of the regions. Seems okay. In terms of what that looks like, so again, truth estimate from 10% sampling. Here is sort of the actual real integral values over all of the regions, and estimated integral values over all the regions. If I was dead on that line, everything would be perfect. I like that curve quite a bit. Makes you feel good. Here's the residual plot. And of course you can see exactly what's happening here, right? It's lost that high frequency sinusoid term, right? And so, like for example, this guy, right? It lost that guy, not showing up, and so of course we're underestimating. But that's what's happening. Now, in terms of how this performs on real data, unfortunately, the couple of ACS variables I've looked at, and of course I haven't looked at anywhere near like a reasonable significant portion of them, because there are tens of thousands of them, it's not performing quite as well, possibly because the assumption of this model is wrong, right? For some things, like population, you can say, well, I'm okay with thinking of there being a population density over which I'm integrating and getting population. But for some other values, like the one I showed you to start with, right? The North Carolina median household income, right? Median household income as a spatial integral of some underlying field? That's math, I mean, that, as a modeling choice, that's okay, but in terms of interpretability, that's a little squiffy. We're not getting garbage results, we're still getting decent stuff, but it's not quite as nice as the simulation just yet. Maybe need to figure out some ways to tune it, or maybe just decide whether our data makes sense for the context of the problem. But that's where we're at so far. Questions, comments, concerns? Oh gosh,
I'll start. If someone is in,
I'll start.
yeah.
Sorry. I guess so at the beginning you said that collapsing your spatial data into the centroid of each of those regions was an unappealing notion. And so I guess I'm wondering why the assumption that there's this underlying field is perhaps a less gross assumption?
Yeah.
Or is it perhaps that taking advantage of the integral transform is appealing?
Well, I mean, so the thing about lattice Krieg is it was developed by climate scientists, right? And it's easy to think of there being an underlying temperature field, right? That's not an unreasonable assumption. For some of ours, and the Tucker McElroy, the census guy we work with, has expressed some reservations on that sort of flow observation model. At this point, I haven't looked at it enough to decide whether it's garbage or not. I feel like there's potential, but it's certainly I'm not without reservation. Okay, that way. Yeah.
super quick, for someone who's been, doing kriging for longer than you've been alive,
I'm sure. Yeah.
you stumbled upon something that's still a problem, is how much of the signal do you think is deterministic and how much is random? And you've chosen a level of deterministicism, right?
Yeah.
So maybe can you give us some insight on where, how many coefficients, how much information you put in a deterministic signal?
Right. Basically, all I have to offer you on that so far is rules of thumb. So lattice Krieg, one of the really nice things about lattice Krieg is it's fast because of that sparse matrix kind of on it, right? That covariance structure. You can get complicated covariance structure that sort of emerges if each basis function only cares about its neighbors. But the thing that's nice about that Krieging problem I showed you guys, if you do it with M Krieg, that takes half an hour. If you do it with L Krieg, it takes about 8 seconds, right? And so you're okay. So for us, the computational expense is pretty small, even if we throw a lot of coefficients at it. And so we're like, well, why not? But yeah, there's always the same regression challenges, right? Overfitting. I'm not strong enough in the math of it yet to give you a theoretically valid answer for it, but at this point, yeah, we got some rules of thumb. Sorry.
There are some really old papers by Grace Wagner where she says if you do know the noise,
Well, yeah.
and you're making here at least assumptions about the noise, then you should be able to also
Yeah.
tune the amount of smoothing in your model that you have there.
Yeah, and we're making some assumptions about the structure of the noise. The thing about ACS is they also generate estimates of standard error, so we can theoretically talk about how much noise we think there is on each of these aerial assumptions. We haven't incorporated that yet, but it's theoretically possible. Yeah. SB, you have anything about that? Okay.
All right. I'm Mike Schmidt. Today we're talking about a Lagrangian method for reactive transport with solid-liquid interaction. And I'm advised by Steve Hankovich and Dave Benson. So brief outline here. We're going to first get into the problem setup. We're going to review a classic 2 years ago, Lagrangian particle tracking method for modeling arbitrarily complex chemical reactions with particles. My goal here with the talk, or our goal in this research, was to develop a method for modeling solid-liquid interactions. These are dissolution, dissolving, or precipitation reactions using these particle methods. Now, a problem with this is that the particles move, and that aqueous species do have to undergo transport. These are like your dissolved calcium ions. But solid species, the calcite that your aquifer is made out of, must not move. Another problem is that just imposing a grid for your particles to move over and then naively just mapping these particles down to that grid would impose overmixing, something we try and avoid with these particle methods. So this means we need some sort of maybe physically motivated weighting scheme for this mass transfer from mobile to immobile particles, we call them. And it sure would be nice if this mass transfer algorithm solved the diffusion equation along the way, because we could use that. The solution we pose in this research is to introduce a method that employs two sets, mobile and immobile particles, that exchange mass via a collocation-based weighting algorithm. So, just first what we're talking about, in a continuous sense, it is the advection-diffusion reaction equation, which for a system of arbitrary chemical complexity, undergoing transport via advection, flow, and diffusion, we have this system of equations where left-hand side is our advection-diffusion equation, advection there, diffusion there, and this is some sort of reaction term on the right-hand side. An arbitrary n number of chemical components can be there with some number of reaction rates that's associated with these reactions. First thing we'll talk about is the distinction between Eulerian and Lagrangian methods. Eulerian methods are grid-based methods for solving these types of equations. That is kind of what I've represented down at the bottom here. These are finite element, finite difference simulations where there are concentrations of chemicals. We have A, B, and C here just at grid points. Here there's none, here there's some, here there's some, and they just pretty much only talk to one of their neighbors. We have a well-mixed volume at each grid point. Whereas the Lagrangian, or our particle tracking simulations, have particles that move. These particles carry these masses, but they actually move in space with the flow and diffusion rather than just transferring these concentrations from one cell to the next. So this arbitrarily complex reactions and particles model, this is what I've based my current work on, is much simpler. This flowchart, don't even need it, but it kind of builds up to the next flowchart we'll see, where we have initial masses on your particles. The particles themselves are transported via diffusive random walks in advection. We perform reactions by treating each particle as its own well-mixed volume, and we do mass balance reactions there. And we have the final masses on the particles. So here's just this cartoon to kind of walk you through how these things work. We have our particles carrying masses of A, B, and C, where they need not be equal, but they each are in chemical equilibrium at the start of a step. So they're transported by advection, just V delta T, based on your underlying velocity grid. They have random walk diffusion, where we draw a random variable for each of them. It's a normal 0, 1 variable, scaled by the standard deviation of that Brownian motion diffusion. That's root 2d delta T, d being your diffusion coefficient here. And then we have a mass exchange, because as I said, these are in chemical equilibrium on their own. So they must first exchange mass between one another, and then we do the balance reactions. So the way that works is each particle has its own position density. Because it's moving by Brownian motion, it's the Gaussian, where it's centered at xi or xj, given the particle, and has that variance of 2d delta t. That means their probability of collocating via diffusion in the next time step is the convolution of those two Gaussians. It is another normal density, average of their two positions, and twice the variance. So they exchange their mass based on that, where we call that collocation density Vs, so the probability that these will be in the same position in the next time step via diffusion. We'll call that 40%, just made it up. But this is how this mass exchange works, but the intuitive sense is if there's a 40% chance they will co-locate, we consider 40% of their mass to be well mixed and they share it evenly. So you can kind of see between this one and this one, no, it doesn't want to change that quickly because of big files. I'm going too far now. Anyway, we consider 40% of their mass to be well mixed and they share that, split it evenly. They don't get 50-50, but 40% of their mass gets split 50-50. After that, we react, and this is just A plus B goes to C, where you see each individual particle, there's more A, so all the B gets consumed, turned into C there. So, now what I've been working on here is this mobile-immobile reactive particle tracking model. There's a few more steps you'll see in here. We start with initial masses on our mobile-immobile sets of particles, two separate sets. Transport the particles in the same way, the mobile ones, obviously. Then we transfer all the mobile masses on these mobile particles to the immobile particles, so all of the chemicals are together to be balanced. Now, oftentimes the reaction equations are formulated in terms of concentrations. It means we have to turn those masses into concentrations, but that's not as important here. Perform those same reactions on the particles we talked about, convert back to masses, transfer those aqueous moving species back to the mobile particles, and our final masses step in time and repeat. So here's my little cartoon for this one, where we have mobile particles moving via random walks in advection up here, and our immobile particles, things say like the rock that your aquifer is made of, call it calcite, maybe dolomite, just down here not moving. So we need to do that mass transfer. We need to bring all of these mobile species down to the immobile particles so we can balance the masses. We'll see what that looks like for just one mobile to all the immobile. Where we see we have the same collocation density when it's really just the position density, since these immobile ones are not moving. See the closest one gets the most mass, furthest the least mass, because this Gaussian weighting scheme for the distribution of mass. We have all the masses come down, and then we balance them into chemical equilibrium again. Then they go back up. We'll see what that looks like from one immobile to all the mobile. Same deal. Closest one gets the most, furthest the least. And then we have our mobile species back up on the mobile particles. Immobile staying down here, not moving. So mathematically, the way this works, our particles are represented in space, in this case, with Dirac deltas. They're just a single point in space. So we can have a continuous representation of our concentration in space for a given time. It's just the mass on a given particle and a Dirac delta centered at that particle's location. So we can represent the mass transfer to a given, just this kth immobile particle from all of the mobile particles. It gets a little bit of mass from each. Even if it's really far away, it's negligible. If it's really close, it's more significant. But the way it works is sum up all the mass with that associated weight based on that collocation Gaussian for the kj pair over the sum. And it's parameterized by the time step you're taking, delta t, where we have these weights summing to 1 for the mobile to immobile transfer, the weights summing over this k index sum to 1, which just means all the mass has to go for every transfer. Alternatively, we can do this all at once with the matrix vector multiplication, where we just have our mobile mass vector, hit it with the weight matrix, we have our immobile masses. And if we want to do a transfer from the mobile phase to the immobile phase and back without doing reactions in between, because we'll later be testing just this mass transfer algorithm, it would be hitting it with both of the matrix. So you have mobile masses at time t, take it to immobile, immobile back to mobile, so that's mobile at time t plus delta t. Or over some fixed period of time, we have our initial mass, we hit it with both those matrices k times, and then we have our mobile masses at time k delta t. So we want to see if this mass transfer algorithm solves the diffusion equation. Thus, we conduct some mobile mass transfers for a variety of conditions. First, do it for equally spaced mobile particles. This is not realistic in terms of our simulations because these particles are moving randomly by these diffusive random walks, but it's an idealized case and we'd like to see good results for the simplest case. In this case, in the paper we do a couple other, or a different condition as well, but we'll just do the Gaussian initial condition in this case, because it's very smooth, it decays to 0 very quickly so we don't get boundary effects, and it's naturally suited to diffusion and has an analytic solution. It's just a wider Gaussian. We'll also do it for randomly spaced mobile particles, simulating these sort of particle tracking transport algorithms. We'll do it again for the Gaussian initial condition, do an ensemble average where we run a bunch of simulations and average the results, and we'll also do statistical analysis just for single simulations. And we'll also check it out for a non-analytic initial condition. So, we check out its sensitivity to the time discretization parameter first, delta t, where the dotted line here is our initial condition. The analytic solution is that red, which you probably can't see at all unless you're in the front row. But my mobile particle tracking algorithm fits the analytic solution quite quickly. It's underneath there, or on top of it rather. But what we see is we're tracking as delta t gets smaller left to right. We want to see our error going down. It's kind of your standard error plot. We have root mean squared error here, where we do see that. It's not all that sensitive to delta t we've seen, but it is going down when we refine things further, which is good. We also see this final jump of a couple orders of magnitude there, where we're positing something like a stability condition operating, where we always see this sort of jump as we violate the stability condition that we're saying, these green dots, when it hits or goes above 1, we see bad things happen. We also check the sensitivity to particle number. Here I am using we're changing the number of mobile particles, and number of immobile particles is always half that. The reason we might do that in a real reactive transport simulation is the chemistry calculation is very expensive. We're only doing them on the immobile particles, so we'd like to do fewer. It would speed things up for us. So this is kind of a case considering what we would like to do in that matter. Same initial condition, and what we see is we increase particle number, make it a more highly discretized case. We see a really sharp drop-off initially when we get into that stable region, and then it ends up just sort of leveling off there, which we compare it to another type of algorithm, which I haven't talked about here, but it sort of approaches the same error as something that is known to work very well for this sort of condition. Now, in terms of the ensemble average, now we see these are the particle positions. You can see that it's not this smooth thing. They're kind of clumpy and very randomly spaced. We just drew from a uniform distribution for the particle positions. And we've done 100 simulations for each value of n here. And then we've kind of chucked them in the bins and averaged the results to just make sure we're seeing the means converge to the expectation here, which we do. We see this is for the most highly resolved case. It's like 12,000 particles, but we do see it sort of, if you can talk about it this way, converging to that analytic solution. And we also do see our errors falling off, though it's less reliable for this case. And we also see that perhaps our stability condition, we might need a little tighter control over that in this randomly spaced case. However, we are seeing, as we increase our discretization, error goes down, so this is good. But thinking about terms, these ensemble average terms may just not even be the right way to think about these things, because kind of expecting these means to converge to expectations in this really noisy simulation might not be realistic. So we took single simulations with randomly spaced particles and just tracked the variance as it grows over time. If these concentrations are evolving by diffusion, it should follow the 2dt, just growing the variance, spatial variance growing by diffusion. We see that it is almost dead on for this case with the Gaussian, so that's another great sign in favor of this. We do it for another non-analytic initial condition where these masses, just the middle 20%, are drawn from a uniform distribution as well, so that we have these just completely erratic gradients rather than that super smooth gradient of the Gaussian. And we see, once again, we have a little bit of error in our variance growth here, but it is pretty darn close, I would say. And finally, just for the full reactive transport model, these are slightly older results before we totally refine this, but we do see that there's blue curves underneath all these orange curves that are finite difference simulations. And this is for, we're injecting a highly acidic CO2-rich brine into an aquifer made of mostly calcite. We see it's about 3.5 coming in. It's initially buffered by the dissolving calcite. Flow is moving left to right here. We see the calcite is dissolving as we go forward in time. This dolomite is a chemical that precipitates behind it. We see it sort of build up in time and then dissolve behind it. And end of the day, the idea is that we have this finite difference solution that we trust, and that using this algorithm, we are getting essentially the same results. So it does seem to work in this full reactive transport case. So just conclusions, the mobile-immobile reactive particle tracking mass transfer algorithm appears to solve the diffusion equation with a controllable level of error. This is good because that means the total diffusion system, if you're running with the random walks, can be partitioned between those diffusive random walks and this mass transfer algorithm, then we cover the total diffusion of the system without introducing any specious error. And end of the day, the mobile reactive particle tracking algorithm may be used to simulate complex reactive transport systems, including interactions with solids, in a manner that allows arbitrary resolution of chemical heterogeneity. Thank you. Questions? Yes?
I can't get my head around the mechanics of what's going on here. So, I mean, you call them particles,
Yeah.
mass, but are they moving so slowly that you don't have to worry about particles going like this and bouncing off?
Right. We consider those to be measure zero probability occurrences. Okay. So yes, they sort of, I mean, on 1D case, they're always moving right through one another, which may be sort of a mass conservation problem, but we just kind of brush that under the rug, perhaps.
Well, I'm just wondering, how you can explain that.
Right. Well, when they're represented as Dirac deltas, they do have the zero support. So maybe that's a good question. It's something that does come up, and I wish I had a better answer right now.
I mean, I'm thinking about particles moving around in fluid, and
right.
You might expect them to bounce off each other.
Exactly. Well, the particles is sort of just a convenient name for them. They're not particles. They're moving points. It's like your
terminology.
Yes. Think about. Exactly. I perhaps have not given enough thought to that exact question. Yeah. Thank you. Yes.
You compared it to the finite difference method you trust. What's the advantage of your method over the finite difference?
Right. One is that, finite difference methods always, the grid point is a well-mixed volume. If you want to represent a highly heterogeneous or noisy condition, you're going to need more and more grid points to resolve that heterogeneity. Whereas with particle methods, it's actually the opposite. The fewer particles you have, the noisier or more heterogeneous condition you can represent. To do a perfectly smooth initial condition with particles, you need an infinite number of them to do it perfectly. Whereas you would usually base your initial number of particles on the initial statistics of your system of interest. And based on that kind of covariance or auto-covariance structure, that's how many particles you would use and how you would organize them in space. So that, as well as no numerical dispersion of particles. As you said, or as I sort of alluded to, you just move them by the velocity field, just from here to here, and there's no finite difference in voodoo that causes numerical dispersion.
You compared how expensive it is compared to the finite difference?
Depends again. Particle number is almost completely analogous to number of grid points, so it kind of, your required number of computations scales with particle number, and depending on your simulation, you could have better results or worse results in terms of time with that particles. However, I am next on the list. I want to write a paper about kind of determining optimal particle number for these simulations based on runtime, stuff like this, so can't reliably say you're guaranteed to have a faster or slower simulation. It just kind of depends on what you're modeling in this case, but it does have distinct advantages just from, like as I said, representing heterogeneity and the no numerical dispersion introduced. Anyone else? Thank you.